Hi, I'm Yiwei Song, a master's student from Peking University. It is my honor to present our paper, HERMAS, a human mobility embedding framework with large-scale cellular signaling data. This is a joint work with Rutgers University and IFLA Tech. Let's see the outline of this presentation. I will first begin with the introduction of this paper. With the extension of cellular networks and cell phones, SD become valuable spatio-temporal data. Signaling data are produced by the interactions between cell phones and cell towers, such as phone calls, messages, and internet surfing. In general, the data format of SD records contains timestamp, tower ID, user ID, anonymous ID, as well as the signaling type. On the one hand, cell phones have become a necessity for citizens. On the other hand, SD are recorded by all sorts of cellular activities that may happen any time. Subsequently, the high penetration rates of SD benefit the researchers to investigate human mobility applications. So in this paper, we focus on how to construct an efficient representation learning framework by mining human mobility using SD for many human mobility applications. A lot of work has been done based on different models. We use two criteria to divide them into two categories. Based on the penetration rates, we divided them into a low penetration rates and high penetration rates. And based on the number of applications, we divided them into single application and multiple applications. However, these works have the common weakness that they only focus either on low penetration rates or a single application, limiting the spatio-temporal coverage, which could be addressed by our work. In addition, we have explored new opportunities to mine human mobility derived from high penetration rates of SD. Due to the load balance strategies as well as environmental factors, cell phones are not always connected to the closest cell tower, which means that they may connect to any connectable cell towers based on real-world network loads. We define this phenomenon as the Ping Pong Effect, and the potential connectable towers are as neighbor towers. We then investigate human mobility by mining the context information and the neighbor information provided by Ping Pong Effect. So the contribution of our paper are listed below. Considering Ping Pong Effect, we designed a representation learning framework called HERMAS for SD dedicated to urban-wide human mobility-related applications. And this framework is evaluated by a city-scale SD dataset with high spatial-temporal coverage. Now, we finished the introduction part. Let's go to the system design. An overview of our system is shown here. It is composed of three main parts: preprocessing, mobility embedding framework, noted as HERMAS, and applications. Specifically, SD are transformed into trajectory data as the input of HERMAS after a preprocessing part. HERMAS is a kernel representation learning framework to embed cell towers by a two-stage embedding algorithms. Then we employ a model of recurrent network to embed the trajectory. And finally, trajectory embedding is used as the input to downstream applications as an evaluation of HERMAS. Now let's put emphasis on the embedding techniques in HERMAS. In this section, we learn an embedding for each tower by two parts, context tower embedding and neighbor tower embedding. First, we extract sequential information from individual SD trajectories. We borrow the idea of SIGCHI here. If several towers appear sequentially in an SD trajectory, then we use the cell tower to predict the towers that appear before and after it and embedding them in the same latent space. Next, we extract neighbor tower information brought by Ping Pong Effect. We argue that the connection patterns are perhaps irregular but could be formulated via exploring in the large-scale trajectories. We here model the connection patterns between central tower and the corresponding neighbor towers based on the tangent mechanism. And finally, we sum up the context tower embedding and the neighbor tower embedding into the tower embedding. Now we go to the evaluation part. We first evaluate trajectory similarity measurement, which is used to study whether our model efficiently extract discriminative information from a moving trajectory. Specifically, three distance measuring methods are employed with common metrics: hit rate and recall. So here we see that HERMAS has a higher performance than other baselines, including different embedding techniques or HERMAS variants. Then we also evaluate our model in the scenario of user performing by two classification tasks. Here we import an extra user dataset containing a transit user and traveler users for evaluation, followed by widely used classification methods RF, D-tree, and SIGCHI boost. The embeddings derived from HERMAS outperform other baselines. Now let's see the conclusion part. In this paper, we designed a novel human mobility representation learning framework called HERMAS to embed SD for large-scale human mobility-related applications. Specifically, we designed a representation learning algorithm for the characteristics of Ping Pong Effect of SD, which distinguishes our framework from the previous works. And we also evaluate our framework by a city-scale dataset on two human mobility-related applications. And that's all. Thanks for listening.